Okay, last time we started with introduction to chromatography and tried to describe mathematically first the retention time, then the peak width, and this is where we stopped. So peak width, or in other terms also said efficiency, is described mathematically using 1D interequation, which is the most widespread relationship. And this is where we stopped. So we had a look at the simplified expression. And saw that it yields a curve with a minimum. And also experimentally, we can obtain a curve with a minimum height of theoretical plate. And minimum, or the smallest height of theoretical plate corresponds to the highest efficiency. So the highest number of theoretical plates. Then we also saw the more precise form of 1D interequation. And then we had some questions. And I understood that you had the question, it was about the second term or the second question?
The second question.
Second question.
I know the first term, and it's because of the but before you mentioned that it was also the first one.
But it includes this dp, so this diameter of the stationary phase particle. So this is also included here. And if dp is smaller, then it adds to a smaller degree to the height of theoretical plate, and therefore it will be smaller as a result. Okay, what about the rest? I think we also discussed in the lecture packing column more densely, and temperature increase was where we stopped, right? So what did you come up about temperature increase? Would it increase efficiency or decrease it? In liquid chromatography. This is one opinion. Other opinions?
Maybe influence physical characteristics of the liquid itself.
Okay. Which characteristics?
Maybe it can affect the pressure and the volume of the liquid, but I don't know how to make it faster.
Okay. Definitely, if the temperature is higher, then the pressure on the column will be lower. Yes, but why? Right? According to
dV equal nRT.
Well, it's about liquids. Then this is, I think, not the case. What is the factor?
Maybe the longitudinal diffusion?
Yes, longitudinal diffusion will be affected. That's correct. But again, why? Yes, viscosity, and you said also viscosity. I heard something from here also. Yes, their movement, which also goes to the viscosity. So indeed, the viscosity of liquids is lower at higher temperatures, which leads to lower pressure, but lower pressure is not relevant at the moment. If the viscosity is lower, then the diffusion rate is higher. So the molecules diffuse faster. And this faster diffusion affects which members here? in this equation. Yes, diffusion coefficients in mobile phase mostly. So dm is here and dm is also here. In general, this mass transfer term, so this mass transfer term has more influence than this longitudinal diffusion term. So that mostly this dominates. And if the diffusion is faster, so which way it goes then? If we divide something with a bigger number, then the result is smaller, so h gets smaller, which means efficiency is higher. Indeed. So let's go back here. Increase of temperature increases in efficiency. And which term? It was terms number 2 and 4, but mostly 4. 4 is more important. So terms 2 and 4. I will write it down like this. Okay. After saying this, the last one should be easy. Correct? Decrease. Which terms? The same way, right? 2 and 4, and 4 being of higher influence. Okay, so now we have an idea or some ideas of how to influence the peak width and see how and which parameters affect it. I just realized that temperature also increases the diffusion in stationary phase. If the stationary phase is liquid, then it also influences it. And I'm afraid I didn't mention that this ds at higher temperatures, the diffusion in the stationary phase, which is liquid, is also lower, so it makes the diffusion faster, which means that this member is also smaller, so this also contributes to the increase of efficiency. So number 3 also here. And number 3. Okay, and then some more remarks about Van Dinter equation, but those come from our Moodle. I'm not sure if you had a look. Here we have a tool or material called Van Dinter, and this is the so-called wiki page. We see the Van Dinter equation is also shown here. It also explains what is the height of theoretical plate and how it's related to the number of theoretical plates. So quite a big part of the lecture material is also described here. It also describes those members of the equation and shows that, okay, A is equal to 2 times lambda times dp, exactly as we had in the slide. So there's a figure to describe the eddy diffusion, something that I tried to draw last time. on the slide. Here it's nicer figure. Longitudinal diffusion also described the same way, and also the mass transfer components, including one nice figure. And even a video is here. So this material has been created by former students. So those of you who participated our lecture last semester, then you know that you can choose to change it, and you can make changes to this page. So please have a look at this material. If you feel that it's not quite correct, then feel free to change it. And if you have questions, which would be great, then of course, raise the questions, let's discuss them and try to find the answers. The figures here are copied from somewhere. The figure sources are referenced, so it's not that bad that they are copied, but still I would very much like if the figures would be original. So if you have time and feel like doing it, then you're very welcome to draw our own figures, copy and paste them here in this material, and of course add your name under the figure that you are the author of the figure and you included it there. Yeah. In fact, I found 2 mistakes in this material. They are perhaps not so clearly visible, but if you read carefully and find them, then please raise the question and let's discuss and see if we can make the material better. So it runs in parallel with our lecture slides, but maybe is in a bit better form for learning. Okay. Now, this was about the peak width. Now about peak shape. Now, we mentioned Henry isotherm, which strictly speaking is about gas-liquid equilibrium. Then in liquid-liquid chromatography, we should say it's a linear isotherm. And if this holds, then the peak would be symmetrical. And the peak would have a shape of normal distribution or Gaussian peak shape. If this linear isotherm holds, if there are many factors which cause peak broadening, the factors influence the peak broadening in both directions, against the flow direction and in the flow direction in equal manner or equal strength. And if all the factors influence all the molecules with the same intensity or same probability, so that there is no preferred interactions for any molecule, then we will have a Gaussian peak shape. One example of this Gaussian peak shape is given here. So if you need to model a perfect chromatographic peak, then you can use this formula for Gauss peak shape. Pretty straightforward. But now finding the peak height at peak width at half height is not exactly it's not exactly equal to the this sigma value, and we see that in fact there is a nice factor in between. So yeah, this is the place where some textbooks oversimplify. They say that yeah, the sigma is equal to the peak width at half height, but this is not true. So be careful with this. Okay, and this brings us to the formula for calculating the number of theoretical plates, from where we can calculate the height of theoretical plate. So all comes in steps. In reality, peaks are not so beautiful, and I don't only mean color, or to be more precise, I don't mean color at all, I mean the peak shape. So very often the peaks are tailing. And this example shown here is quite bad, I would say, but it happens relatively often. So that this tailing is quite severe here. All right, to characterize the tailing of peak, then we, well, technical problems again, the peaks are not finished. So to characterize how the peaks are tailing, the peak asymmetry factor is used, and the asymmetry factor is calculated as shown here in the slide. So this is just one way of calculating the asymmetry factor. So we measure the peak height, then take 10% of this peak height, and at this point we draw this distances from the retention time of the peak to the peak, the peak tail and to the peak front, so parallel to the horizontal axis. And ratio of those two lengths is the asymmetry factor. In this image, the asymmetry factor would be 1.96, quite close to 2. So this is almost at the limit of acceptable peak shape. So yeah, peaks are quite often asymmetric. Tailing is a problem because peak resolution, we will discuss peak resolution later, but this is the distance between neighboring peaks. So the peak resolution is worse. Of course, if we compare it with symmetric peaks, then tail may overlap with the neighboring peak, and this is a problem. Then quantitative accuracy is worse because it's difficult to decide exactly where to finish the peak, or where to, up to which point to integrate the peak area. Then limits of detections get higher. Well, with limits of detection, it's interesting because limits of detection mostly depend on the peak height. But of course, if some of the analyte material is distributed over time, then the peak height is lower, and if it's lower, then the limit of detection is worse. Does this make sense? Yep. Wonderful. Okay, but what interests us most is why peaks are sometimes, or even quite often, are asymmetric. So in partition chromatography, partition liquid chromatography, the sorption isotherm is quite often nonlinear. And in reverse phase liquid chromatography, the most common reason for this is that there are more than one retention mechanism at the time. So partition is the retention mechanism that we would like to see be dominating, but sometimes adsorption also takes place. And well, we may ask why. We covered the stationary phase with silanol groups, so there should be no stationary phase or no solid surface available for analytes. But there still are. So the C18 groups, which are most common in reverse phase chromatography, they cover only a fraction of the surface of stationary phase. So let's say roughly 50% of silanols are actually reacted with those C18 tails. So the rest being still free. And also metal cations, which may appear in silica gel particles as impurities. And those have been shown to be of a big problem, which caused a lot of peak tailing. So, yeah, we will see this after perhaps a month, that in fact nowadays the modern silica production produces mostly high purity silica, and those metal cations in most cases are not that big of a problem nowadays. So it used to be a big problem perhaps 30 years ago, maybe even more, but now it's mostly solved for most chromatographic systems, columns. Yes?
Is adsorption different than partition? Like, is it permanent more or less?
Permanent doesn't exactly play a role, but adsorption is meant on the surface, and partition goes within the bulk of the material. We will deal with this a bit more, but yeah, partition is most or easiest to understand if we think of two immiscible liquids, like in liquid-liquid extraction. We have two liquids which do not mix with each other, and molecules can partition between those two liquids. In case of adsorption, we have a liquid phase and solid phase, and molecules can adsorb on the surface of a solid material. So it doesn't go in there, but on top of the solid layer. And as the surface area is rather limited, then this is one side of adsorption difference. And another is that depending on the model, we will see those adsorption models soon, every site on the solid surface can bind just one molecule. So it's restricted there. Yes, please.
If the last class we were talking about, for example, if we have a partition method and it's a column where it's the solid carrier covered by a stationary phase of this liquid, but how can these processes compete the absorption and partition in the same system? It's because the stationary phase doesn't cover completely the solid carrier. That's why we have
exactly.
competition.
Yes. Let's imagine that this is the surface of a silica gel particle. We have those silanol groups here. Well, let's draw many of them. And if now we convert this silica gel particle into a reversed phase, stationary phase, then we replace one of those silanol groups with this C18 chain. I draw it very simplified at the moment. And it will have also some side groups, which are methyl groups usually. This C18 chain, however, is of so big volume that it doesn't allow another molecule to react here, but instead the other one can react only here. So this one will still be active here, and also here and here, and those can participate in this adsorption process. Yes, it can be deprotonated. Yes. So this depends on pH. We will see this also.
It will always be the case, like even though our column is the newest one, we always gonna have it.
Yes. Yes. So in all those reverse phase columns, there are quite a big number of silanol groups available. And okay, let's go slide by slide. There's more. Okay, so mostly the stationary phases are based on silica gel. So on the surface there are silanol groups, as I tried to draw them. And when we produce those reverse phase columns, then these silane groups are attached to the surface. And we see that it attaches to the surface so that this R group is the C18 mostly, and two methyl group, which I tried to draw here, are also present. Okay, I omitted this silica atom, which is shown in the slide. Okay, the fuller is the derivatization, the better, of course. The more of those silanol groups react, the better, but always quite a significant part of the silanol groups remains underivatized or not covered. And they are called residual silanol groups. Silanol groups can be of 3 or maybe even 4 types. Isolated, geminal, vicinal, just depending on to which silica atoms the hydroxyl groups are attached. Well, why is it important to see the difference or to know the difference? Because those groups have different pKa values. At the moment, we don't need to go into detail with those pKa values, just that those pKa values are, in most cases, or very often, somewhere around pKa 5, let's say. The range, which is denoted in the literature, is from 3 to 15, which is very broad. Usually from 5 to 8, but I would say around 5 is the most common that we see. So that pKa values around 5 mean that if the eluent is more acidic, then it's protonated. So the pH is lower than 5, then it's protonated. If the pH of the eluent is higher than 5, then it's deprotonated and becomes negatively charged. All right. Now, metal cations, those enhance the absorption even more. So the metal ions may be free. Well, this D here refers to this figure here. So as in figure D, so metal ion may be just near the surface of the silica gel and be free there. Or it may also be embedded in the lattice of silica gel, and then it also alters the acid properties of the silanol group, the neighboring silanol group, and makes it usually more acidic. Okay, now how can we minimize the effect of those problems, so metal cations and silanol groups? Against metal cations, acid washing used to be the method to clean the silica gel, so metals dissolved in acid, and this way we got rid of metal ions. Well, it has to be performed cautiously because we may hydrolyze some of those silanol hydroxyl groups, sorry, not hydroxyl, alkyl groups from the stationary phase. So, okay, but as I said, metal cations nowadays with modern columns are usually not a big problem. Silanols still are, and to cope with silanols, mostly two methods are used. One is end capping. End capping is the process where smaller reactive molecules are attached to the surface. For example, the one which has just methyl groups, so it may be, okay, now I have to write this silica here also, like this. I will add the silica everywhere. So now this molecule is small enough to fit into this space between the two big ones, and it just reacts with the silanol group, and now it's covered. It cannot dissociate anymore. It's not available for absorption. This is one way, but even after this, there will be considerable number of free silanol groups in molecules. Just some of them are too close, and even the small molecule does not fit here. So in order to somehow shield also those silanol groups, then so-called shielding is used. So instead of methyl group in this molecule, bigger, more voluminous molecules are used, as for example, tertiary butanol group, which is big enough to cover the space above this silanol group so that analyte molecule just cannot access it anymore. So in this case, the silanols will still remain there, just they are not accessible for analyte. Okay, now back to this adsorption. This kind of adsorption to either metal ions or silanol groups. This affects mostly polar compounds. Polar compounds can interact with polar groups more strongly, and therefore polar molecules are mostly affected, and especially basic compounds. Basic compounds, because they are positively charged at the acidic environment, they are positively charged, then positive-negative interaction is the strongest here, and this influences the absorption most. Adsorption. So we can imagine that if the pH of the eluent is, let's say, around 6, then this silanol group will be, let's take this one. This silanol group will be deprotonated, it's negatively charged. And if we have an analyte which is base, and this base at pH 6 is protonated, then it may be some amine, for example, NH3 with plus, and of course they interact strongly and cause tailing of the peak. Another group of molecules which is very prone to tailing is those which can complex metal ions. So if metal ions are at the surface of the silica gel, then the complex are formed, and this causes another interaction in this system. So we have two sorption processes. First, partition in the liquid volumes of eluent and even the stationary phase liquid here, this C18 phases, those are relatively high volume. And analytes have sufficient space in those, so the linear isotherm results in. For adsorption, there are quite limited number of adsorption centers. Only fractional analyte molecules can be adsorbed on those sites at a time. And therefore, part of the molecules is affected by adsorption and, of course, partition at the same time, and another part is affected only by the partition. And as adsorption is usually stronger than partitioning, then the molecules which undergo adsorption, they lag behind, causing tailing. Okay, so we need to speak about the models for adsorption. And again, we have some assumption for this. Adsorption only occurs at adsorption centers. And in that case, we speak about monomolecular adsorption. This is the simplest adsorption model. There are different models, but let's stick to this simplest one. Then analyte molecules do not interact with each other. So if the concentration is low, then this holds quite well. The number of centers is limited. Indeed, usually the number of those adsorption centers is rather low compared to the number of analyte molecules. And we also assume that all the centers are energetically equivalent, so they are equal energetically. So adsorption to this site is equally strong as adsorption to this site. This is the energetically equivalent. More assumptions. There are two processes that run simultaneously, adsorption and desorption. And they can reach equilibrium. So then the adsorption is said to be at equilibrium. The rate of adsorption is proportional to the number of free centers available on the surface and the number of non-adsorbed analyte molecules in the liquid phase. We will see it on the next slide how this is expressed mathematically. And the rate of desorption is proportional to the number of occupied centers. Of course, the more of those molecules are there on the surface, the more they, or the faster they can desorb. So first, this adsorption and adsorption rate, how fast the adsorption goes. This depends on some sort of adsorption coefficient, the rate constant for the adsorption. Then concentration of analyte in the mobile phase. Quite clearly, the more analyte is present in the mobile phase, and the faster is the adsorption to the solid phase. And then there is a difference. So maximum surface concentration of analyte molecules. So we could say that this is the number of adsorption centers on the surface of the solid phase in this stationary phase. And then the second is surface concentration of analyte molecules. So how much of those adsorption centers are occupied. And of course, their difference is the amount of free adsorption centers. So in brackets, we have the amount or the concentration of free adsorption centers, then molecules which can be adsorbed, and there, if we multiply those and the constant of adsorption, then we get the adsorption rate. Now, desorption takes also place, so molecules can be desorbed from the surface, but this only depends on the surface concentration of analyte molecules. Quite straightforward that it only can be related to this quantity. Okay, and clearly, if those two processes are in equilibrium, then those rates are equal. And if we derive this formula further, then we rearrange to obtain that the concentration of molecule adsorbed equals and depends on the rest like this. We can introduce the adsorption equilibrium constant, which is the ratio of two adsorption and the desorption coefficients. And after using this, we have derived the Langmuir isotherm mathematical expression. So it's relatively simple algebra, I would say. So if you don't feel sure about this, then I really recommend that you start from the beginning and try to derive it. just to get more used to those ideas. Yes, please.
Is this like the one should be in brackets?
This number one.
Yeah, like is it multiplied by k or just one
This is as it's in.
Because in the last.
What is it? Numerator. Everything is in numerator, so the brackets could be from here to here.
I mean, like if we go up, previous, right?
Uh-huh.
It was like k ads was outside. And yeah, I think it took like kds as common, so like the other c and one should be in brackets.
Well, in order to use this equilibrium constant, then we could divide numerator and denominator by k des by this value. And if we divide to this one, then we can substitute it with the absorption equilibrium constant. And dividing this by k des gives also the equilibrium constant. And if we divide this by k ds, then we obtain number one.
Okay, so should it be in brackets?
No. Because the way it goes is like this, that what we do is we divide both of them. So let's divide using those dots. And that goes A and this. And also here goes K this. Yes, it's lowercase k, yeah. Okay. Mm-hmm. All right. So Langmuir's isotherm, and the formula is shown here. Now, analyzing it graphically, then we see that if the concentration in mobile phase is on the horizontal axis and concentration which is adsorbed on the surface is on the vertical axis, then this adds max, well, which I said that in simplified terms, it is the number of adsorption sites. So the number of adsorption sites, this in a way gives us the maximum how high this graph can rise. It cannot have more molecules than the number of sites. So if this adds max equals 10, then it approaches 10. If the adds max approaches is 5, then the maximum can be 5. So the curve approaches this value, and this absorption equilibrium constant. This only tells us how fast we reach near this maximum value. So the bigger is the absorption equilibrium constant, the faster we reach near the maximum value, which all makes a lot of sense, I would say. Okay. Now, if the number of centers is large compared to the number of analyte molecules, then the isotherm can be approximated by the Henry isotherm. So it becomes similar, so almost linear. If the number of centers is small, then almost all of them are occupied, exactly as we saw here at the end of the curve, that most of them are occupied. Now, Langmuir isotherm has its drawbacks in describing absorption. It's just a model, as usual. And as we know, all the models are wrong, right? But some are useful, indeed. Yes. So it's a model. Its assumptions do not hold 100%, just to some extent. And the problems with those assumptions are that they are not energetically equivalent. Molecules interact among themselves. Absorption can occur on molecules which are already adsorbed, so bimolecular absorption. And so all the points that, or all the assumptions that we made in principle can be wrong. But still, even with this simplified model, we can still make some conclusions. So the overall absorption isotherm is not linear. So we have this partition isotherm, Henry isotherm. Not quite correct to call it Henry because it's not gas we are talking about, but okay. So partition isotherm, then the adsorption isotherm is with the green line, and the mixed isotherm is shown here, the uppermost. So it's nonlinear. And if we consider its effect on peak shape, then we see that ideally if it would be only linear, then the peak shape would be Gaussian. But the more absorption-desorption processes are involved, the more tailing the peak will be. So as the absorption-desorption processes are stronger, then those molecules delay, and the more absorption-desorption processes take place, the more are they delayed. So the tailing is longer. Yes?
In one of the slides, say if the number of centers is large compared to the number of analyte molecules, we can the isotherm can be approximated by the Henry. But the Henry isotherm is like the ideal case, no?
Yes.
So why, if we want to avoid the absorption and desorption processes, why, if we have a larger number of centers available, why is it better to achieve this?
So in principle, you suggest that let's make a larger number of absorption centers available for molecules, then the situation would be better, right? Was this?
That's how I understand this phrase.
Yeah.
If you have like higher number of centers that create the absorption and desorption, you will get into the ideal case, but in real life, it's completely the opposite. You get the ideal case with partition instead of absorption.
Yeah, this would apply nicely if we had a chromatography with adsorption only. But even if we make more adsorption centers available here, then we will still have two processes, the partitioning and adsorption, which have different strengths, and then we would have a tailing peak. So this sentence, yeah, now I understand. Perhaps it's not very good to point it out there, this sentence. that this holds nicely when we want to use purely adsorption chromatography. Yes, only adsorption. Just, let's say, pure silica gel, and we want to perform a chromatography on just the silica gel surface.
So when we are using reverse chromatography, we try to avoid as much as possible the absorption and destruction process. No? So
Exactly.
having a higher number of these centers will make our peak more heavy.
Yes, exactly. Yes. Mm-hmm. Okay, and now, in conclusion, the chromatographic process should be based on partition with linear absorption isotherm, and then we would obtain symmetric peaks. And if we want to achieve this, then either there is no adsorption centers, or the adsorption centers are somehow hidden, let's say. Either they are, the access is hindered, like here, or they are covered by end capping. Mobile phase additives is another way of making the adsorption centers occupied. And now I see again that changing the slide format has left the arrows pointing to a wrong thing. So occupied, this is here. And the stationary phase must be of high quality, low number of residual silones and metal cations. This goes there. And yeah, this is not correct. More conclusions. In adsorption chromatography, we use adsorption chromatography. The work should be done in the Henry region, meaning in adsorption chromatography, we should try to work at those conditions where the isotherm is linear. And for this, there should be large specific surface area, so a lot of adsorption centers. Centers should be energetically similar. If we think of silica gel, then this means that with minimum amount of metal impurities. And only low concentrations can be analyzed. Well, this is quite common in analytical chemistry that we aim at low concentrations. In reality, it's almost never ideal. Tailing is quite frequent in adsorption chromatography. Is why? Can you guess what are the reasons? Right? Because of
Absorption more like.
yes, but this is adsorption chromatography now. So this is purely adsorption chromatography, but still the peaks are quite often tailing. Even though, sorry?
The analytes are meter-thing more strong in absorption process.
Yes, and the reason is that the centers are not energetically similar, so that the this is one of the problems mostly that one place on the stationary phase holds the molecule stronger than other spot. And with solid materials, it's very difficult to achieve a situation where they would all be equal. So there are different silanols available. Okay, and partition chromatography is definitely more popular than adsorption chromatography, just because we have bigger chances to get symmetric peaks, non-tailing peaks. Tailing is more pronounced with analytes which adsorb stronger. The reason is exactly what I said. So the ones which remain strongly adsorbed, if the sites are not energetically equivalent, then the longer those molecules stay in the stationary phase and are retained a longer time. So both because of silanol groups and metal complexes. Okay, we had a look at only one adsorption model. In fact, there are many more. Freundlich-Jomkin, so-called BET isotherm, but we don't need to dive all those. We just saw that the simplest one, Langmuir's, is sufficient. And finally, how to describe peak shapes in chromatography. There are many mathematical formula derived for this. Most of them which are listed in this article are empirical ones, so not based on exactly rationalizing why and which interactions cause it, but it's just mathematical expressions how to describe peak shapes. And many formula have been proposed. They describe unsymmetric peaks. Some are able to describe also double peaks. So quite nice mathematical formula are presented. Why do we need those models, although empirical ones, for understanding the process for peak deconvolution? Deconvolution is the process where the peaks which are not nicely separated are separated, let's say, mathematically. And I can try to explain it. Let's say that we have a chromatogram with two peaks overlapping. Let's say one of them is like this and another here. And now if we have a mathematical formula to describe their shape, then we can calculate that this peak is actually like this, symmetrical one, and this one is actually like this, oh, like this. So just by approximating or by approximating them to some curves, then it's possible to find out the real peak area for those compounds and still to continue the analysis, even though the compounds are not well resolved. So this was peak deconvolution and also for simulating chromatographic or simulating chromatograms, let's say this way. This also makes use of those formula. Okay. So far, so good. Okay, I don't see any questions. Then let's go closer to chromatography. So there are many types of liquid chromatography, and in this course we will discuss some of them. So reversed phase, of course, and this is the object of most attention. And under there is also so-called ion pair chromatography, which we explain a bit, but don't go into very much details. Normal phase chromatography, hydrophilic interaction chromatography, ion exchange chromatography, size exclusion, chiral chromatography. So we discuss all of them briefly, but not very much, but mostly reverse phase chromatography. So why is reverse phase chromatography so popular? Here is one scheme of how to select good chromatographic method, or let's say suitable chromatographic method for particular analysis. And the first scheme is for analyte molecules with molecular mass below 3000. And if the molecule or the substance is soluble in organic solvents, then if it's soluble in methanol and water mixtures or acetonitrile and water mixtures, then definitely we will use reverse phase chromatography. If it's soluble in THF, tetrahydrofuran, then reverse phase chromatography. If the molecule is water soluble, then if it's non-ionic or if it's ionic, still we use reverse phase chromatography, reverse phase liquid chromatography. And there are only few occasions where, well, I would say we cannot use reverse phase chromatography and are forced to use something else. If the analytes are of high molecular mass, so higher than 3000, then if it's water soluble, then we can still try reverse phase liquid chromatography, but the rest is about the size, the exclusion chromatography. Okay, but let's continue with the most popular one, the reverse phase chromatography. And it's recognized by the fact that the mobile phase is polar and the stationary phase is non-polar, related to each other. It is the most common liquid chromatography type. It has been estimated that about 75% of all chromatographic analyses are performed in reversed phase chromatography mode. And we mostly focus on this after we pass all the others also, right? So stationary phase is non-polar. Most commonly, some alkyl chains are attached to the silica gel particles. This is the typical reverse phase stationary phase. And most commonly, it's CAT. So octadecyl groups are attached to the silica gel surface. Mobile phase, in turn, is polar, and the most common solvents for mobile phase are mixtures of water with methanol or water with acetonitrile, or, well, those two are the most common ones. Sometimes also tetrahydrofurane is used, but this is not, by far not as common as methanol and acetonitrile. Sometimes, or even quite often, some additives are used. They may be really buffer solutions, but in liquid chromatography with mass spectrometric detection, very often it's just some acid which is added. So strictly speaking, we must not call it buffer solution, although you can see it quite often that the table lists eluent additives and buffer solutions used in LCMS, and under buffer solutions we can see that it's just simple acid, which by definition is not buffer solution. But okay, let's just accept this inaccurate terminology. Okay, the strength of those reversed phase eluent solvents. Their strength is different, and the solvents are ordered in so-called heliotropic series. And this heliotropic series is quite well known for normal phase chromatography based on silica gel. So epsilon zero values are quite well known. Heliotropic series are also used in reverse phase chromatography, perhaps not that widely known, but still useful. So what does it tell us? This applies to the C18 stationary phase. So those values and this order, this depends on which stationary phase is used. And if the stationary phase is C18, then methanol has a value of 1, and acetonitrile is 3, which means that it's stronger. CHF is even stronger, isopropanol even more so, and dioxane is by far stronger than any of those. So it means that if in the eluent we would replace methanol by isopropanol, then all the retention times would be very much shorter, because the heliotropic value for isopropanol is much higher. Okay, now a bit of another term which we will use quite extensively in this course is about the strong eluent component and weak eluent component. So strong eluent component is the component which makes the analyte to elute earlier. So if we increase the percentage of the strong eluent component, then the compound or the analyte has shorter retention time. So if we take the most common mixture of water and acetonitrile, then if we increase the percentage of acetonitrile in the eluent, then the retention time will be shorter. Therefore, acetonitrile is called strong eluent component. And water is then weak eluent component. So, yeah, please try to get used to it, because we we make our communication much shorter and more clear if we use those terms. Then it's easier to explain. And if we have to say every time that, okay, we have to increase the percentage of acetonitrile or methanol or THF or whatever we use as the modifier or the organic compound, then it makes it quite long. We increase the percentage of organic of a strong eluent component. Everybody knows. Okay, now interactions in reversed phase liquid chromatography. Here we first mention that mobile phase molecules, mobile phase to mobile phase molecules, they have strong interaction. Mobile phase is polar, and polar molecules interact strongly with another polar molecule. So their interaction is strong. Analyte and mobile phase molecules also, the interaction can be quite strong, as the analyte is to this polar side, definitely. Analyte and stationary phase have weak interaction. And this is the place where even some textbooks, they claim the opposite. They claim that, yeah, those analytes which have strong interaction with stationary phase. Well, interaction with stationary phase is not strong. So be careful and note this when you read this. And mobile phase and stationary phase also, this interaction is quite weak. Here, one way may ask then, why does the analyte even partition into stationary phase? If the stationary phase and analyte interaction is weak, so why does the analyte go to the stationary phase? Just because the mobile phase, this interaction is so strong that the solvent molecules, well, energetically, it's favorable to interact by themselves, just solvent molecules with solvent molecules, and they push the analyte molecules out from them from the bulk of the solvent, and they push it into the stationary phase. Energetically, it's favorable because yeah, the gain of energy is the highest. Okay. Again, some clouds are missing. All right, then let's complete this drawing together. So, stationary phase in reverse phase chromatography, is it polar or non-polar? Stationary phase is non-polar. Let's see where we go. Stationary phase, non-polar. Let's mark it somewhere here. Eluent. Is it polar or non-polar? But even the most organic rich eluent, even if it's just pure methanol, then it's still quite polar. So the eluent is definitely polar. So I will mark this here. What about analytes? Are the analytes polar to the polar side or non-polar? Polar, yes. Okay, if analytes are too polar, then they are not retained at all because the interaction between eluent molecules and analyte molecules is so strong that they are not pushed to the stationary phase. So the analyte has to be just polar enough. If the analyte molecules would be non-polar, then they wouldn't like to come to the mobile phase, or the mobile phase would push them out to the stationary phase, and they would remain there for a very long time. So the retention time would be very long. If we would use non-polar solvent for elution in reverse phase chromatography, then all the molecules would elute very fast. Retention times very short. If the eluent would be very, very, very polar, let's say water, just pure water, then the retention times would be too long, so long that we won't see anything eluting from the column. If stationary phase would be polar, what then?
Not reverse.
Yes, indeed. Then we're not speaking about reverse phase chromatography. So this drawing will be here later. All right. One example chromatogram. Yeah, the structures are distorted. Okay, mobile phase is acetonitrile and water mixture, allocratic elution. The analyte molecules are shown here. It's a series alkylphenone compounds. And just the first one is uracil, this kind of compound, which is very, very polar, elutes the first from this column. And then C3-alkylphenone, so it would be propyl group here, then butyl group, and so on. And we see that the peaks elute later if the alkyl chain is longer, which is exactly what we know, that if the molecule is less polar, then it's retained longer. Why is it retained longer? Yes, exactly. Please don't say that it interacts strongly with the stationary phase. It's pushed out from the mobile phase, and indeed it stays for a longer fraction of time in the stationary phase. That's true, but this doesn't mean that the interactions are particularly strong with the stationary phase. Yes?
Can you use the word comparatively when you're saying this?
Yes, yes, absolutely. Okay, the hydrophobicity of molecules is important, and here you will see one series or one chromatogram of different compounds. And we can spend quite some time on discussing why one compound has shorter or longer retention time than other. Quite interesting, I think those first three is rather interesting. We see that it's just they differ in the position of the hydroxyl groups. And the first one has shortest retention time. If they are in meta position, then it's average, and ortho position has the longest retention time. Yes, this probably plays a role here, that this is possible. But perhaps it's simpler to say that this molecule can, let's say, those are the P18 chains on the silica gel surface. Then this molecule can insert its aromatic ring here, and the OH groups are pointing out. But the other structures, as the even this para isomer, it's not possible. It cannot insert the aromatic ring so deep in between those. Yes, yes, exactly. So that, yeah. But I would say we could try to describe in detail and explain it here. And then somebody comes and says that, okay, let's still use reverse phase chromatography, but different eluent, and everything is different. So yes, it's possible to explain, but don't take it too seriously at this point. There are points where we can take it seriously, but here we can't go into too deep details. After saying this, I will show in Moodle, and I will make it available now. So this phenols, this material. So, considering exactly the same chromatogram and factors which affect the retention, and then octanol water partition coefficients, and then comes the point that I mentioned. So there are paranitrophenol, paradinitrobenzene, nitrobenzene, methyl benzoate. So 4 compounds, and both chromatograms depict reverse phase chromatography. In one case, the eluent contains water and methanol. In another case, water and PHF. And we see that the peak ordering is 1, 2, 3, 4 in one case, and 4, 3, 2, 1 in another case. So it's not easy to explain both of them. So yes, it's a good training to try to explain the charges and intermolecular and intramolecular bonds and everything. Yes, it makes sense. But don't be surprised when at the end you will see that, well, in one case it's one way and in another case it's opposite.
Maybe related to PHF here. Okay, so
yeah, well, definitely this example is carefully selected and exactly to demonstrate that that the order is completely reversed. But the phenomenon that with acetonitrile we see the peaks one way and with methanol the other way is quite common. So this is the selectivity of eluents. Okay, perhaps simpler and more straightforward is the effect of strong eluent component percentage on the elution. So here we have a series of chromatograms with different percentage of acetonitrile. So strong solvent component is increasing the percentage. And we see that the retention times of all the peaks get shorter and shorter as we increase the percentage of acetonitrile. Quite expected. Okay, shall we continue? I'm afraid the lecture time is over, so I could continue, but I'm afraid you. Yeah. Anyway, if you have questions, then you feel free to ask, because we just finished this first topic or first part. Everything is clear. That's wonderful. Okay, then this homework, look at the Van Dinter page, this wiki page, and try to find and spot the mistakes there. And yeah, you are very welcome to improve the drawings and add additional material if you wish. So check it out there. Okay, thank you, and see you next week.